gentlemen, this is the second video in the series. This one here will be based on unit number 7. The first one was unit 2. The last one was unit 6. And now we're on unit 7, which is parallel circuits. And one of the best ways to describe a parallel circuit is to describe how it's different from a series circuit. And a lot of you, I know this is review, but just bear with me. In our series circuit, if you remember, I totally had just one pathway for electrons to flow. They couldn't go any other way. They didn't have any other pathway they could use. And so, golly geez, because the electrons had only one pathway to go, every bit of the circuit's element would dictate the amperage and make it the same everywhere. And so that's why in a series circuit, I have a circuit constant that is I, or amperage. Okay. Now, parallel circuit, which is actually a lot more like what we use and what we install every day, is a circuit that doesn't just have one pathway. So like in this case, if we got rid of these, we would have a series circuit with just the one resistor. But it actually has many pathways for our electricity to go. So in there, I was just trying to expand it a little bit, but you can see then you've got that and you've got this pathway. Every pathway or branch needs to have resistance on it. Otherwise, you would have a short. So, series circuit, one pathway with a circuit constant of amperage because there's only one way for the amps to go. And a parallel circuit has many pathways, like I'm drawing again. And the circuit constant, because there are many pathways, is actually voltage, or E. All right, so that's the first thing you have to keep straight in your head. Series circuits, amps stay the same. Parallel circuits, voltage stays the same. And then, like I said in the last video, I like to use the term circuit constant. So for a series circuit, the circuit constant is amps. And for a parallel circuit, the circuit constant is voltage. And that actually works to your advantage because when you look at the types of questions that are in the quizzes and tests, when you get a series circuit, they always ask you to find IT. They're always trying to see if you understand that concept that IT in a series circuit equals I1 equals I2, etc. Okay. And so they may have you figure out what I total is, which I showed you in the last video, and then ask you what the amperage is. When I say I2, I'm saying that it's the amperage over R2. In the series circuit, it's going to be the same, the whole circuit. Okay. In the parallel circuit, that's not at all the case. If we have voltage as our constant, then there's this weird interplay between voltage and amperage where they switch places. Like I said, amps stay the same, or a circuit constant in series circuits, where voltage is the circuit constant and stays the same in a parallel circuit. Okay, so voltage doesn't add up in a parallel circuit. Amps does. So say we have half an amp here and half an amp here and half an amp here, we would add those up to get 1.5 amps. And what that would look like is 1.5 amps would be our IT, and the math problem would look like this: IT equals 0.5, and would say that's not R, but I1 plus 0.5, which would be I2. So anytime we're asked about a part of a circuit, if anything's numbered, like we have R1, and they ask us for I1 or E1 or even W1 or power P1, it's always associated with whichever value you have. So that would be all twos, that would be all threes, and obviously anything that says T is the total. All right. So key differences. We can go ahead and get rid of our series circuit because we're talking about parallel circuit math in this video. And so there are some really funky, wonky things. And to be perfectly honest with you, the best thing you could do for yourself is to get the Uglies book and go through those first pages and do the math on your calculator, because that's the way you're going to become solid in it. You can sit here and try to figure out why things are the way they are, but in the end, if you can't do the math, you can't do the math. Okay. Voltage stays the same. So ET equals E1 equals E2, etc. in a parallel circuit. Amperage, IT adds up. So I1 plus I2 plus I3. Okay. So we kind of get those. Those make sense. But where parallel circuits get a little bit confusing is that we have to add the resistance up differently. And the reason is because every time you add a parallel branch, you are adding additional pathways. So if I extend the circuit out, you're adding additional pathways for electrons to flow. And it has what we call an inverse effect on the resistance total. So that means I can make I can make at least one hard and fast statement about a parallel circuit that only has resistance. And that is that RT is always going to be less than any one resistor in the circuit. So RT is always going to be less than R1, or it's always going to be less than R2, or it's always going to be less than R3. Okay, it's never going to be more. As we add additional paths, or if we have more than just the one branch, that right there would be, if all we had was that, it would make it a series circuit, right? Get rid of that series circuit. Okay. So the way that we add up this resistance is not by simply going R1 plus R2 plus R3 like we would in a series circuit. That's not going to give us the answer. It'll give you frowny faces because everybody makes that mistake for parallel circuits. But we can't add it up that way because remember I said that as we add branches to a parallel circuit, it inversely affects the resistance. And so we use this term called the reciprocal, and that's what we add up. Okay. So a reciprocal is going to be kind of the opposite of a whole number. Okay. So say we have 200. The reciprocal of 200 can be simply described as a 1 over 200. All right. So now we have basically the opposite of 200, which is 1/200th. So the smallest and the largest, if that makes sense. Let's give ourselves some values here. Let's say R1 is 10, R2 is 20, and R3 is 30. And we needed to add these resistances up. Okay. We wouldn't be able to just go 10 plus 20 plus 30 equals 60 like we could in a series circuit, because, like I said, each pathway inversely affects the circuit, so that RT is always going to be less than 10, then 20, then 30. Okay. So how do we add that up? The best way is for me to show you on the calculator, but let me show you a visual representation of that. RT equals the reciprocal of 10, which is 1 over 10, plus the reciprocal of 20, which is 1 over 20, plus the reciprocal of 30, which is 1 over 30. Another way that you can draw that is the -1 exponent button. Okay, so -1 plus 30 is -1. And really, this kind of math is easier done in a calculator. And so let me go ahead and open that calculator up, and let's get some stuff cleared out so that we can have a fresh start. I made a video earlier and this wasn't quite working the way it needed to, so hopefully I fixed that. But if you'll look down in this area, that's where my keystrokes are going to be. And then, of course, you can see the screen. We could actually do both, though I'm not as familiar with this calculator as I am with the one that I ask my students to get. But we can do 10 and reciprocate it by using the -1 exponent button, and then 20 1 over, or -1, and then do the 30 -1, and then hit enter, and we get this weird number 0.183, and we can't really use that. That's not actually what we're looking for. So we actually, and this is the part that people mess up on, you actually have to reciprocate that small number, and in the end you get the number that we need. In this case, it is 5.45454545 forever. So we could definitely just call that RT equals 5.5, right, and just round up. Or we could keep it more detailed and do 4, 5, right? 4. Or we could just keep going until we get it all the way. So that is actually the total resistance for this parallel circuit. And like I said, right, it is smaller at a 5.5 than any other part of the circuit. Okay, so it doesn't need to be this complicated. There's actually several methods of doing this that the book wants you to know. And so let's do the easy one. So the easy one would be to say, hey, we've got 3 resistors in parallel and they're all the same. Okay. What would be our RT? Well, we could do it on the calculator. Let's get everything cleared. That would be 10. Hit the -1 button, 10, -1 button, plus 10, -1 button, and hit enter. And we get 0.3, but that's not our actual answer. That's our actual answer, 3 1/3. Well, isn't that just 10 split 3 ways? It is 1/3. So RT is 3 1/3 is a way of saying it, or 3.333. Okay, how about we get one that's a nice number that's divisible by 3, because that may help us understand just a little bit better. So 12, 12, and 12. If we have 12 on each resistor and we have 3 resistors, it's just as simple as taking 12 and dividing by the number of resistors, and the number is 4. Okay, so that's one way you can do it in your head. And let's do a proof of concept on the calculator. 12 to the negative first plus 12 to the negative first plus 12 to the negative first equals 25.25. And if we do the negative first of that, which we're changing it from a reciprocal to a whole number, we do get the 4. So hopefully, between these first 2 videos, you guys have a really good grasp on parallel circuit math. There's a few other methods in the book, but what I typically do is, if I can do this method, I still double check with the calculator just like I did. So, all right, hopefully that answered more questions than it caused you to ask. But that, and then hopefully seeing it on the calculator and seeing it drawn out also helps. That's one of the reasons why I want to do these videos. Just remember, in a series circuit, because there's no other pathway for the electrons to flow, the resistance just adds up. It just stacks up against those electrons that are moving. But in a parallel circuit, because the electrons can choose different pathways, it doesn't stack up. It actually reduces the amount of resistance on the total circuit. And it continues to the more you add. So thanks for watching. Hopefully this one turns out.